All right, so I'm Archie. That's not my real name, it's just a nickname. And I'm going to talk to you about the piezo preamplifier, which is a little project of mine. So first things first, who am I? I'm originally a web developer. I do front-end, JavaScript, stuff like that. But over the years, I've started doing electronic music, and then I started wondering like, what are all these magical boxes on my desk made of? So I started disassembling them. And then it occurred to me that maybe I could even create my own, or at least copy some designs I liked. And since then it has become a sort of a dream that maybe if I continue doing this for some time, then maybe someday I could work in an audio hardware industry, which is like much more interesting than the JavaScript stuff. So these are a few examples of stuff I did, like a distortion pedal or a MIDI through box or an analog mixer and stuff like that. It's basically just what I was able to, understand. And when I started doing this, I was doing it on a strip board or a Vero board, which looks like this. It's basically just a pre-made board which has holes in it, and you can like solder the through-hole components onto it. It's very, very, very good for quick prototyping, and it's pretty stable, but also it can get quite messy. So if you have something smaller, like a smaller sub-oscillator or something like that, it's quite okay. But already in this MIDI through box, you can see the wiring can get quite messy, and even more so in the distortion pedal. And once I got onto the analog mixer, I realized that I basically have to learn PCB design because this is unmanageable. I could not debug this if anything happened. So I needed to come up with a project to learn PCB design, and the project was electrifying a kantele. So kantele is a very basic stringed instrument from Finland. This is basically a very cheap small kantele. It's a child's toy. And on the picture it has already been electrified. It already has well, by electrifying I mean turning the acoustic instrument into an electric instrument, something that I could plug into other pedals or an amplifier or a sound card or something like that. So this is a picture already after the work, but yeah, it was just an acoustic instrument. And so the first thing you need when you want to electrify an instrument is some kind of a pickup or a microphone. So I chose the contact microphones, which work with piezoelectricity, which is basically you can transform acoustic vibrations into electronic charge. So basically you have a piezo microphone which you glue onto the body of the instrument. That's why it's called a contact microphone. And the microphone will then transform the vibration of the body to the electronic charge. You can buy those microphones. This is a cheap one from AliExpress, but you can also create your own. You just need the piezo discs, a few bottle caps, a little bit of wire, maybe some glue, and a little bit of soldering, and you can create your own. So that's what I did. Piezo microphones, their basic model is just AC source with a capacitor which is in series, and this capacitor is in the range of nanofarads, so basically like 10 nanofarads, stuff like that. And this also means that the output impedance of the piezo microphone can get very high, and that's the reason why you need a piezo preamplifier, so that you can like plug the microphone into something that you can then plug into the later stages, like in other pedals or stuff like that. So when we talk about piezo preamplifiers, you basically have two options. You either have very high input impedance, which is much higher than the output impedance of the microphone, or then I found another option on the internet, which is called a charge amplifier, which paradoxically enough has a very low input impedance, and it's not very common in audio industry. It's much more common in scientific instrumentation and accelerometers and stuff like that. So it should have a few advantages over the high input impedance approach. Namely, you need some kind of a cable between the microphone and the preamplifier, and this cable has a certain capacitance. And this capacitance can basically affect the frequency response of the microphone or the gain maybe, but with this approach, with charge amplifier, it should have no effect Also, the triboelectric effect should be reduced, which is the noise of the cable when it is moved. And also supposedly a 5060 mains hum pickup should be reduced. So I decided to try the charge amplifier, which looks like this. On the left you have the piezo microphone with some cable capacitance. And on the right there's the charge amplifier, which is, well, I'm not going to explain it in great detail, but nor am I going to like pretend I understand it completely. But it's basically just an inverting op-amp in an integrator configuration. So basically, this component, this feedback capacitor, it's the most important component of the circuit, and it sets, together with the piezo capacitance, it sets the gain of the circuit. So the ratio of the piezo capacitance and the feedback capacitor sets the gain of the amplifier, and that means that when you want to change the gain of charge amplifier, you will need to change the capacitance in the feedback loop. So that's the theory. So for the first version of the preamp, I chose this basic block diagram. The microphone goes into the charge amplifier. Then I decided to add some tone control, so just treble and bass knobs. For this I had chosen Bastl, which is pretty omnipresent, and a simple volume knob, and an audio jack from which you can go to the next stages, like a pedal or a guitar amplifier or something like that. So Bastl tone control is pretty basic stuff, like pretty normal stuff. It just allows me to change the bass response or the treble response in the range of like plus minus 10, 12 decibels, so nothing drastic. All right, so in order to prepare, I decided that the piezo preamplifier should be powered by 9-volt battery, because that's still pretty common in the guitar pedal world. And for this 9-volt battery, I wanted to add some kind of an LED battery indicator, something that would basically tell me if the battery is going to die out, because it is a nightmare to find out in the middle of your concert that your preamplifier has died and you need to change the battery. So I added an LED that would tell me if the voltage of the battery has gone below a certain level. And then I also needed to add op-amp biasing, because I have only a single-sided supply, only plus 9 volts, so I need to bias the op-amps. So I drew the schematic in the KiCad and simulated it in LTSpice, blah, blah, blah. And then I moved on to the breadboard. So I'm pretty sure many of you know this view, like a complete mess. You just do something on your breadboard, and then there's like everything around, like even a wood glue or whatnot. Miraculously enough, it worked. So I moved on to the next stage, for which I turned back to my old friend, the strip board. So this is how I butchered the Kantele. As you can see on the left side, there's the circuits of the project, and also the battery, also the do-it-yourself piezo microphone from the bottle cap. On the right side, you see the top side of the instrument. There's the volume knob, the LED for the battery indicator, the bass and treble potentiometers, which are very uncomfortably close together, very hard to operate, and also the output jack. So, all right, this is the first version. It kind of worked, but it had a few disadvantages. First of all, it's still a strip board, so not what I set out to do. It's not a PCB. It has fixed gains, so there's no way to change the capacitance of the charge amplifier. It's glued and drilled onto the instrument, which is something nobody would want to do with their instruments. So yeah, this instrument was basically ruined, but it was cheap, so don't worry. And yeah, there's no enclosure. So yeah, for the second version of the preamplifier, I had these ideas to finally learn the PCB design. So I chose a 4-layer PCB because it would allow me to make it smaller, the final product. Also chose the SMD technology because for the same reason, and for the reason of it being able to be manufactured by the manufacturer or pre-assembled. I wanted to add an enclosure, also an input jack, so that the microphone could be switched easily, because in the previous version the microphone went directly into the board. Now when I have an input jack and an output jack, I also added some kind of an ESD protection, so a TVS diode or something like that. And Yeah, a switch to switch the gain. So basically a switch that would enable me to change the capacitance in the feedback loop of the charge amplifier. Also a high-pass filter, because I realized that sometimes you need to remove the low-end boominess of the instrument. And also a switchable backsandal center, which I'll explain in a bit. So the frequency characteristic, without the high-pass filter, the preamp should have like a flat response in the audio spectrum. With the high-pass filter, you can like gently roll off the low end, which is a very simple first-order filter, nothing special. And what I mean by the backsandal tone control with switchable center, this is the image we have already seen. This is the backsandal. And I basically wanted to do this. So with a switch, you can just move the center of the tone control knobs, so you can adjust the ranges on which the treble and bass knobs operate. So it would make it like more usable with other instruments. Anyway, this is the block diagram for the second version. So now we go into the input jack, like piezo input jack. Then to the charge amplifier, then to the high-pass filter, and then the backsandal and the volume knob as before. All right, so the second version finally looks like a PCB, and miraculously enough, it also worked with a few modifications. And I was also able to put it inside an enclosure, but yeah, there were more disadvantages. So, for example, the potentiometers were quite wiggly. They had like really cheap feel to them. The switches, which are like on the back, you cannot even see them because they are very small. They are hard to operate, especially in an enclosure from the backside. It was pretty nightmarish. Also, there is no on-off switch. The whole circuit is switched just by the output jack, by inserting a cable into the output jack. And the enclosure is a pre-made enclosure. I had to drill manually and write on it, and it was very imprecise. It was a lot of work and a mess. So for the third version, I decided I need better potentiometers, larger switches, integrated battery holders so that I could just attach it to the product. Also a dedicated on-off switch with true bypass, which is kind of unnecessary, but it's easy to do. And also a proper DC input, because not everyone wants to power the preamp from the battery. Maybe someone wants to power it from the pedal board. So when I have a DC input, I also added a reverse polarity protection, which is also quite unnecessary, but I just wanted to learn how it's done. And also some very basic power supply filtering and a nicer enclosure. All right, so the last block diagram, I promise. You go into the piezo input jack and then onto the on-off switch with true bypass. And since like after that, it's basically the same as the second version: amplifier, high-pass filter, backsandal, and volume knob. All right, so the third version, that's the render in KiCad, and that's the army of them. As you can see, I had to use other potentiometers, and I didn't have enough space on the board, so I had to use wires again, which is a lot of work. But I was quite satisfied with it otherwise. But I haven't shown you the enclosure yet, so let's talk about that. I decided I don't want to drill enclosures anymore because it's a complete mess. It's always imprecise, so I decided to basically use aluminum PCBs to print them out and to join them together, like join the 6 sides of them together, which would also allow me to do some kind of a PCB art, or maybe print out the text so that I don't have to write it myself. And maybe also would allow me for the enclosure to be able to be somehow mounted on a guitar strap if necessary. But I didn't know how to do this, so first I had to like study a lot and read a lot of forums and discover PCB art in itself. Then I made these 2 ugly test PCBs that you've already seen. This basically allowed me to just, check the manufacturer's capabilities. So I just send them these 2 boards, or it's just one board, but in 2 colors. And it allowed me to see the quality of the result and also test various techniques of doing PCB art. So you can create your own images on your silk screen layer, on the solder mask, on the copper layer, or on the core directly. You can use various like solder fields which are continuous or hatched. You can use various like cutouts. I also tried experimenting with the border radiuses of the cutouts to see what is possible to be milled out or what isn't. Various like protruding flanges, stuff like that. So this is it's very ugly, but allowed me to test the waters, and I played with it so for such a long time that I extracted everything I learned into a blog post on my website. So if you're interested in creating like PCB art or using PCBs for front panels, this is everything I have learned. You can find it on my website, which will be in the at the end of the presentation. All right, so this is the third version of the preamp. As you can see, it's just 6 sides, aluminum PCBs joined together. It is a slightly more professional than the previous enclosure. Also allowed me to pester my girlfriend to draw me some frogs. And well, yeah, basically there also should be an advantage with regards to ESD or to electromagnetic emissions, because it is aluminum, and you can like basically ground the whole enclosure onto the main PCB at a certain point, and maybe it would help. I don't know. Anyway, so this is the final third version, and probably I'm not going to do any more. So the conclusion of the project is that I learned a lot, and I know the preamp works, but the question is how well, because I'm not much of an acoustic player anyway. It was just a project to learn, and I can do some measurements in free software like Visual Analyzer and REW, which will allow you to measure the frequency response to test that the design is correct, and also maybe measure the total harmonic distortion and stuff like that. But are measurements enough in this sort of project? Because the problem is I don't have any other piezo preamplifiers to compare it with, nor do I have any professional piezo microphones. So this is something, yeah, I'm not sure. Also, it hasn't been battle tested on stage, because I know there's a big difference between something that sits on your desk and something that's on stage, where you have like vibrations, temperatures, humidity, stuff like that. And when I sum down the BOM costs and imagine some kind of a retail price, I realized that it's not economically viable to make it in small batches, but that wasn't the initial goal anyway, so I'm okay with that. Anyway, I made a few of these, so if you fulfill all 4 of these requirements, if you own an acoustic instrument, if you have a piezo microphone at home, if you have a different piezo preamp to compare it with, and if you are willing to test and share the test results with me, then I can give you a whoop. Probably died.
It died?
Yeah. Or maybe.
Sorry.
Then yeah. So if you fulfill all 4 of these requirements, I will give you a preamplifier and you can try it out. So anyway, this is my website, and thank you for listening. And if you have any questions, I can pretend I know the answers. So, any questions?
You. Very cool. Thanks.
Thank you.
Can I can't. I wanted to just ask, like, how you chose the tone centers for the Baxandal, because my first thought was, because most of these piezo discs, they have a resonant frequency.
Yeah.
But it's usually above 1 kilohertz. But technically, if you would put the tone center like into that range, you could also kind of reduce that resonant frequency.
Yeah, that's the problem with piezo discs, that they have different resonant frequencies. But also, what I found out that it's it's basically pretty impossible to test them, like to test the actual frequency, and also that when you stick or when you glue the piezo disc or the piezo microphone onto the body of the instrument, then the frequency changes. So it's basically pretty difficult to determine where the resonance is. But as for your question, how I chose the tone centers for the backsandal, I just went through various different designs of backsandals and like, whoa, what was that? La la la, I don't know. Oh, maybe this one died too.
Please continue.
So I just went through different designs from different tone stacks on the internet, and I just chose 3 frequencies, which are like I think it was like 350 hertz, 60 hertz, and 1 kilohertz. So it's basically independent, or I haven't. I didn't take the resonant frequency of the piezo disc into the consideration, just the usual tone stacks, so that it could suit as many instruments as possible. So yeah, that's.
Great. Yeah, I would be willing to test.
That's great. So I'll have at least one people